Welcome to the Linkfiddy's Another Deep Dive. Today, we're going to be taking a really close look at this paper, Scalable Optimization of Large Scale Architecture for Reasoning. It's a pretty dense paper, but I think it's really important for data scientists and researchers who are, interested in how LLMs can be trained to reason more effectively. Before we begin, we would very much appreciate it if you like and subscribe to continue receiving more deep dives like this.
Yeah, absolutely. And you hit the nail on the head there. This paper really tackles a fundamental challenge in the field. How do we go beyond the limits of just simple chain of thought prompt, which is so common in LMs these days?
Okay, so that's chain of thought, right?
Right, exactly.
Can you give us a quick refresher, for the listeners who might not be as familiar with chain of thought prompting? What is that, and why is that a limitation?
Sure. So chain of thought prompting, or COT, as we call it, is basically this technique where you're guiding the LLM to solve a problem step by step, almost like you're writing out a thought process. And it's been pretty effective, for straightforward tasks. But when you start dealing with more complex problems, things that require branching logic, exploring multiple hypotheses or just connecting ideas in a way that's not linear, COT kind of falls short.
So, it's like trying to navigate a complex maze. But you can only walk forward, right? You're going to miss all those crucial paths. Maybe even get stuck in some dead ends.
Yeah, that's a great way to put it. And that's where the Solar framework comes in. The authors of this paper, they recognize that, hey, different problems, they need different reasoning structures, or what they call topologies. And they say that ideally LMM should be able to choose the most effective topology, on the fly for whatever problem they're facing, whether that's chain of thought or tree of thought or even graph of thought.
Okay, so we've COT, chain of thought, TOT, a tree of thought, and GOT, graph of thought. Can we break those down a little bit? So the OT, I think we have a good grasp on that now, but to go, what are those all about?
Yeah, so think of it this way, as like following a recipe step by step. You're just going in a straight line, to, on the other hand, is more like making a decision where you have to weigh different factors. Consider the pros and cons of each branch before moving forward. And then GOT's a graph of thought that's like exploring a whole network of interconnected ideas, jumping back and forth, making connections that aren't necessarily linear.
That's a great analogy. I think that really helps to clarify things. So, the researchers behind Solar, they're basically saying, hey, these other approaches, TOT, tree of thought, and GOT, a graph of thought, they can be just as effective as COT, a chain of thought, if not more so, for certain tasks.
Exactly, and they set out to prove that.
So how did they go about doing that?
Well, the first thing they did was they tested this hypothesis, right? Page 2, they talk about how they evaluated these different reasoning topologies using, the Quent VL7B instruct model. They specifically chose this model because it's known for its ability to handle these more complex reasoning structures beyond just GOT. And they tested it on two pretty challenging mathematical reasoning datasets, MATH and GSM8K.
MATH and GSM8K. Okay, so these are like industry standard datasets for evaluating reasoning capabilities in LMs. Right.
Yeah, exactly. They're tough. They require the LM to not only understand the problem, but also to reason through multiple steps to arrive at the solution. No easy feat.
So, they ran these tests, put these different topologies head to head. What did they find?
Well, that's where things get interesting. They introduced this concept of win rate on page 7, which basically measures how often a particular reasoning topology was the best performing one for a given problem. And what they found, and this is shown in figure on page 13, is that even though LLMs, they tend to default to the less commonly used structures like TOT, a tree of thought, and GOT, a graph of thought, actually perform just as well in terms of accuracy.
So even though like TOT, Tree of Thought, and GOT are kind of the underdogs in the LLM world, they're holding their own against the reigning champ, COT.
Right, and what's even more interesting is that, as you can see in Figure 4 on page 14, different problems actually favor different reasoning topologies. Some problems were better solved with COT, others with T, and others with GOT. So there's no one-size-fits-all solution here. It really highlights the need for a system like Solr that can adapt to the specific problem at hand.
Okay, so that brings us to the heart of Solr, right? This idea of enabling LLMs to dynamically optimize their reasoning process. On page 2, they lay out this core idea, how to make LLMs smarter by letting them choose the best reasoning topology.
Yeah, and they propose this two-pronged approach. First, they introduce this Topological-Annotation-Generation system, or TAG for short.
Yeah.
TAG is basically an automated system for creating training data that's specifically designed to help LLMs learn how to select the best topology for a given problem.
So, TAG is like a what a robot teacher. It creates these practice problems, but it also tells you which reasoning strategy is most likely to lead to the right answer.
Yeah, exactly. And then the second part of their approach is what they call the Topological Scaling framework. Yeah.
This is a set of techniques for training and optimizing LLMs to effectively leverage these different reasoning topologies. So it's like, teaching the LLM not only how to solve problems, but also when to use which reasoning strategy. It's giving it that metacognitive ability.
Okay, so we've got TAG, which is all about creating the right training data. And then we've got topological scaling, which is about actually training the LLM to use that data effectively.
That's it in a nutshell. Let's dig into TAG a little bit more. On page 7, they describe this system in detail. Can you walk us through how it works? Like step by step what's going on under the hood.
Sure. So imagine you have a bunch of problems, right? And you want to figure out, okay, which reasoning topology works best for each one. COT's a chain of thought, TOT, tree of thought, or GOT's a graph of thought. That's exactly what TAG does. It takes a problem as input, and then it actually uses an LM to generate responses using all three topologies.
So it's like having the LLM try out all the different tools in the toolbox.
Exactly. And then based on how accurate each response is, TAG assigns a probability to each topology, indicating how likely it is to lead to the correct answer. They call this the top 2 label. And then they also use a hard label, which is a simple binary labels other one that tells you whether a generated answer is correct or not.
Okay, so the 2 label is like a measure of confidence, right? Like, how sure is TAG that this particular topology is the right one for this problem? Got it. And then they define a hard problem as one where all the topologies have a topo label below 7. So essentially even TAG is struggling to figure out which topology is best for these problems.
Right. And they actually found that this definition of hardness correlates really well with human judgment, which is pretty cool. Like they had humans read the difficulty of problems, and then they compared those ratings to the topo labels assigned by a TAG, and there was a strong correlation. This is shown in Figure 2 on page 8. So it suggests that TAG is not only generating useful training data, but also providing some real insights into what makes a problem difficult in the first place.
So it's like TAG is tapping into something fundamental about problem solving. Something that we humans intuitively understand, but haven't really been able to articulate.
Yeah, there's something really profound about that.
Okay, so now we've got this labeled dataset generated by TAG. What happens next? How do they use this data to actually train the LM to reason more effectively?
That's where the topological scaling framework comes in. It's described on page 9 as a hierarchical pipeline. Basically, it's a series of steps that take this labeled data and use it to optimize the LM's reasoning process. The first step in this pipeline is what they call topological tuning.
Topological tuning. Okay, so what's happening during topological tuning? Are they like tweaking the model's parameters or something?
Yeah, they're essentially fine-tuning the base LM using the high-quality data generated by TAG. Remember, TAG tells us which topology is most likely to be effective for each problem. So, during topological tuning, they're exposing the letter M to this data, and it's learning to adapt its reasoning strategy based on the specific characteristics of each problem.
So, it's like giving the LM specialized training on a whole range of different reasoning strategies, is learning not just how to solve problems, but also how to choose the right strategy for the job.
Exactly. And they go into more detail about the implementation on page 10. They talk about how they carefully selected and prepared the training data. Using techniques like diversity sampling to make sure they had a good mix of different problem difficulties and correct answer filtering to keep only those responses that were labeled as correct by TAG.
So, they're really focused on quality control, making sure that the LLM is learning from the best possible examples.
Yeah, absolutely.
And they use the Qwen2 VL70B instruct model as their base and fine-tuned it using the LoRa technique.
Right, LoRa, which stands for Low Rank Adaptation. It's a really clever way to make these huge language models more manageable. Instead of retraining the whole model from scratch, which would take forever and cost a fortune, they're just fine-tuning specific parts of it. It's like a targeted upgrade.
So instead of rebuilding the whole engine, they're just swapping out a few key components to make it run more smoothly. That's a good analogy.
And what were the results? Could topological tuning actually lead to, better performance?
Oh, absolutely. In Table 1 on page 17, they show the results of their experiments. Topological tuning led to a solid 5% improvement in accuracy, which is significant. But what's even more interesting is that it also led to shorter answers, especially for those more complex problems.
Wait a minute. So, training for better reasoning actually made the LM more concise. That seems counterintuitive, yet is a little surprising. But they hypothesize that this is because the model, by being exposed to a wider range of reasoning strategies during topological tuning, learns to identify the most direct and efficient path to the solution. It's like it's learning to cut through the noise and focus on the essential information.
It's almost like it's developed a better sense of when to stop thinking and just give the answer. Yeah.
Like it's learned the value of brevity.
Yeah, I like that. It's like, in writing, sometimes the most powerful sentences are the shortest ones. Okay, so topological tuning is all about training the LLM to be a more adaptable reasoner, choosing the best strategy for the problem at hand. But they also introduced this other technique called topological rewarding. What's that all about?
Right, topological rewarding. So this is a really interesting approach. It's all about making the LLM a smarter decision maker during the inference stage.
So instead of just blindly applying a reasoned strategy, the LLM is now equipped to evaluate its options and choose the best one for the specific task at hand. This sounds really promising.
It is, and we'll dive into the details of that after a quick break.
Sounds good.
So, topological rewarding. Yeah, it's all about giving the LLM that ability to kind of, think on its feet and choose the best reasoning strategy at runtime instead of just sticking to one predetermined approach.
So it's like instead of always using a hammer, the LLM can now look at the problem and decide, maybe I need a screwdriver for this one.
Exactly, and they achieve this through what they call the multitask topological reward model, or M-TRM.
M-TRM. Okay, so it's multitask, which implies it's doing more than just picking the best topology, right? What else is this M-TRM up to?
Right, so the really cool thing about M-TRM is it doesn't stop at just choosing the topology. It also evaluates the candidate answers generated by each topology and picks the best one overall. It's like a judge who's assessing both the reasoning process and the final outcome.
Okay, so it's like not just how you get to the answer, but also the quality of the answer itself. M-TRM is judging both journey and the destination.
Precisely, and as you might expect, this approach works really well. On page 15, figure 6 shows how M-TRM outperforms these single task reward models that were trained to do either topology selection or answer ranking separately.
So, by combining those tasks into one multitask model, they actually get better performance than either task in isolation. It's like the whole is greater than the sum of its parts.
Right, and they dive even deeper into this analysis on page 16. They explore different ways of training M-TRM, like using different base models, different training data, and so on. Table 4 shows that using a stronger base model, specifically the Quinn 7B model, gives them better results. They also found that training M-TRM on data from all three topologies rather than just one improves performance across the board.
So it's like the more variety you give it during training, the better it performs later on. Makes sense.
Exactly. And they're very transparent about their methods. Appendix E lists the specific hyperparameters they used. So if anyone wants to replicate their work, they've got all the details.
That's great. That kind of openness is so important in research.
Absolutely.
Okay. So, we've got this M-TRM, this multitasking judge that can pick the best reasoning path and the best answer. But how does it actually work in practice? Like when the LLM is trying to solve a new problem. How does topological rewarding come into play?
Sure, so imagine the LLM is faced with a new problem. The first thing it does is generate multiple candidate answers using all three reasoning topologies, COT, TOT, and GOT. Each of those topologies produces its own set of reasoning steps and a final answer.
So it's like having three different teams of experts, each with their own approach to solving the problem.
Exactly. And then M-TRM steps in. It looks at the reasoning paths taken by each topology and the final answers they produced. Based on that evaluation, it picks the winning combination, the best reasoning path, and the best answer.
So it's a reasoning competition, and M-TRM is the ultimate judge. It gets to decide which approach wins based on both style and substance.
I like that analogy, and they found that this topological rewarding approach led to a pretty impressive 9% accuracy boost compared to just using GOT.
9%. Wow, that's a big improvement. And you know, they tested topological rewarding both with and without topological tuning. And in both cases, it led to big gains.
So it seems like even if you don't tune the model with that special training data, just having this intelligent selection mechanism at runtime can make a big difference.
Yeah, that's a really key takeaway. It shows that letting the LM dynamically choose its reasoning strategy is a really powerful idea. Okay, so we've got topological tuning, which trains the LLM on a diverse set of reasoning strategies, and topological rewarding, which uses M-TRM to guide its decisions in real time. But you also mentioned this thing called hybrid scaling. What happens when you combine those two approaches?
Right. So hybrid scaling is like the ultimate power-up. It takes the fine-tuned model from topological tuning and then applies topological rewarding during inference. So you're getting the benefits of both specialized training and intelligent decision-making at runtime.
It's like giving the LLM the best of both worlds, a rigorous training program, and a personal coach to help it make the right decisions on the fly.
Exactly, and as you can imagine, this leads to even better results. They found that hybrid scaling led to a whopping 102% improvement in accuracy.
10.2, that's you said.
It really seems like they figured out a way to make these LLMs much more powerful reasoners. I agree. But of course, this level of performance comes at a cost. Hybrid scaling is the most computationally expensive approach both during training and inference.
Right. Makes sense. You're doing more calculations at every step. But if you need the absolute best accuracy and you've got the computing power to spare, it seems like hybrid scaling is the way to go.
Absolutely. And they're very upfront about this trade-off in the paper. Table 1 on page 17 shows the accuracy and latency for each approach. you can see that topological rewarding and hybrid scaling give you the biggest accuracy gains, but they also take a bit longer to run.
So, it's like anything else. There's a trade-off between performance and efficiency.
But this table is really helpful because it lets you see those trade-offs clearly and decide what's best for your particular use case. Okay, so let's shift gears a bit and talk about how they actually evaluated these different approaches. They used two datasets, MATH and GSM8K, which are both focused on mathematical reasoning. Why did they choose those specific datasets? What makes them so challenging?
Well, they chose MATH and GSM8K because they're considered to be really tough benchmarks for evaluating reasoning capabilities. MATH is a data set of math problems, while GSM8K is a collection of grade school math word problems. And these aren't just your simple arithmetic problems. They require the LLM to really think through the problem, break it down into steps, and apply logic to get to the answer.
So these are problems that would actually challenge a human, not just a calculator.
Exactly. And they found that across both data sets, all three topological scaling approaches consistently outperformed just using GOT by a significant margin. That really supports their main idea that dynamically choosing the right reasoning topology can really boost performance.
So it's not just a theoretical idea, it actually works in practice.
Right? And beyond just the overall accuracy improvements, they also made some interesting observations about the different approaches. For example, they found that topological tuning, as you can see in Figure 5 on page 14, led to shorter answers, especially for the more difficult problems. This suggests that by being exposed to all those different reasoning strategies, the model learned to be more concise and get straight to the point.
It's like it's learned to be more efficient with its thinking.
Yeah, exactly. And to make sure these improvements were really because of the multi-topology training, they did what's called an ablation study, which is described on page 15.
Ablation study, that's where you basically remove parts of the system to see how it affects performance.
Right.
So, in this case, they wanted to make sure that those accuracy gains were really because of the topological tuning and not just because they were fine-tuning the model in general.
Exactly. And their study showed that the multi-topology training was definitely a key factor in the improved performance.
That's good, solid evidence. Okay, so we've covered a lot of ground here. We talked about the motivation behind Solar, the technical details of how it works, and the really impressive results they achieved. But they don't just stop there, right? On page 17, they have this whole discussion section where they start to look beyond these immediate results and consider the broader implications of their work.
Yeah, that's where things get really interesting. They start to connect the dots and paint a bigger picture of what all this means for the future of LLM research.
Okay, so let's dive into that discussion section. What are some of the key ideas they bring up? What are the big takeaways?
So, yeah, they start talking about how Solar could be applied to, a wider range of tasks beyond just math. They argue that this idea of dynamic topological reasoning, it could be really beneficial for any task where an LM needs to kind of like reason through complex information and make decisions.
So it's not just about like solving equations. It's about, making LMMs more intelligent in a broader sense.
Exactly. And they even touch on this idea of resilience to overthinking, which is kind of fascinating.
Yeah, I noticed that too on page 17. It's not like the main focus of the paper, but it's a really interesting observation. What do you think they mean by resilience to overthinking?
Well, they noticed that topological tuning, in addition to improving accuracy, it also seemed to make the LLM less prone to kind of, going down rabbit holes and getting bogged down in unnecessary steps. It's like by being exposed to all those different reasoning strategies, the LLM learns to identify the most efficient path to the solution and avoid those unnecessary detours.
So it's like instead of overthinking the problem, the LLM is learning to think more strategically, more efficiently.
Right? And they suggest that this could be a really fruitful area for future research. Like, can we intentionally train LLM to be more resilient to overthinking? Would that lead to even bigger performance gains?
It's like we're starting to understand not just how to make LMs smarter, but also how to make them think more like humans do.
Yeah, there's definitely something to that.
Okay, so let's jump to the end of the paper, page 18, where they wrap up their discussion and present their conclusions. What are the key takeaways they want us to remember?
I think the biggest takeaway is that solar is a really significant step forward in how we can train LLMs to reason more effectively. It's not just about making them bigger. It's about making them smarter and more adaptable.
Right? It's about giving them the tools and the training they need to tackle a wider range of complex problems with more accuracy and efficiency.
Exactly. And they highlight the key innovations that make solar so effective, like the Topological-Annotation-Generation TAG system and the hierarchical topological scaling framework.
And they also acknowledge that there's still a lot more work to be done. They mentioned several exciting directions for future research, like developing better reward models, exploring new applications of dynamic topological reasoning, and so on.
Right? There are so many possibilities here. This paper is really just the beginning of a whole new chapter in LM research.
Well, there you have it. A deep dive into solar scalable optimization of large-scale architecture for reasoning. We've explored the limitations of traditional chain of thought prompting, uncovered the power of dynamic topological reasoning, and seen how the solar framework is pushing the boundaries of what LMs can do.
It's been a really exciting journey, and I think this research has the potential to revolutionize how we think about and build intelligent systems. A huge thank you to our expert for walking us through this fascinating paper, and to our listeners for joining us on this Linkvities deep dive. Please subscribe to our channel and like this video if you truly did. Thank you. Until next time, keep exploring and keep learning.
Absolutely, always keep learning.